focused on series with positive terms. When we talked about the comparison test, the limit comparison test, the integral test, all the series were positive. The terms were positive, otherwise you cannot use these tests. We have seen some series with negative terms when we talked about the special series like the geometric and the telescoping. Okay. Now in this section we will consider a series where the term will alternate between positive and negative values. Okay. So this type of series we're going to call it alternating series. So an alternating series is a series whose terms alternate between positive and negative values. Here's an example. Sum from n equal 1 to infinity, negative 1 over 2 to the power n. This is a geometric series. We've seen this before, but when you write this explicitly, you will notice that you start with negative 1 half plus negative 1 half square, which is plus 1 over 4, plus negative 1 half cube, which is negative, plus negative is plus, so negative 1 over 8, and so on. So this is an example of an alternating series. Here's another example. So it's not necessarily that it has to be negative 1 to the n. No, it could be negative 1 to the n plus 1. It could be negative 1 to the n plus 2. It could be anything. Remember, like for example, if you got negative 1 to the n plus 2, that's the same as negative 1 to the n. And the reason is very simple, because this is negative 1 to the n times negative 1 squared. So this is just 1, so that's negative 1 to the n times 1, which is negative 1 to the n. Okay. So you can always write it in this way, like negative 1 to the n or negative 1 to the n plus 1. So these two are examples of alternating series. So this is the general form. Every alternating series will be written in this form. It's not necessarily that it's going to start at 1. It's not necessarily that it's going to have negative 1 to the power n. It could be negative 1 to the n plus 1. It could be negative 1 to the n plus 4, n plus 2. This doesn't matter. But what we care about is that that term that you write here by itself must be positive. Okay, so this is a positive term. So the negative 1 to the n or negative 1 to the n plus 1 will take the role of the sign, sometimes positive, sometimes negative, depends on the values of n. Okay. So Bn is greater or equal to 0 for all integers n. So now we will give a test called the alternating series test. This test will allow us to determine whether a series is whether an alternating series is convergent or divergent. Okay. So first of all, we're gonna have an alternating series. Remember that the Bn here is a positive quantity. So the alternating series converges if I have these two possibilities, these two conditions. The first condition is that the Bn has to be decreasing. Meaning what? Meaning that Bn is bigger than Bn plus 1. Okay, so each term is bigger than the next term. Like for example, B1 is bigger than B2, B2 is bigger than B3, and so on. So the function has to be decreasing. The function of Bn has to be decreasing. And the limit of Bn must go to 0 as n goes to infinity. If these two conditions are satisfied, then the alternating series converges. Okay, so these series converge if these are satisfied, and that's what we call the alternating series test. Now we want to prove this. The proof is nice. It's not very simple, as you will see, but it's something good to know. So we're going to assume that Bn is greater or equal to 0, and assume that it's decreasing. So I want to show that if Bn is decreasing and if its limit is equal to 0, then the series is going to converge. So here I'm considering Bn. I'm assuming that Bn is decreasing. That means Bn plus 1 is less than Bn. Okay, like for example, B2 is less than B1. So I can use the fact that, for example, B1 minus B2 is bigger than 0, and so on. So I'm writing here the sums explicitly. Notice that I'm alternating between the colors blue, green, and the ones with blue are the ones with the odd indices S1, S3, S5, S2n minus 1, S2n plus 1, and this keeps going. So I'm writing this explicitly. If you try S1, you're going to make k equal 1 up to n equal 1. So that's going to be negative 1 to the power 2 times b1, which is just b1. S2 is b1 minus b2. So when you write this explicitly, you're going to get these forms. Okay. Now I want to take, remember we talked before that the partial sums, they form a sequence. So I do have sequence here. But I want to consider two different sequences. I want to consider the sequences S to N. So the ones with the even indices, and I want to consider the sequence S to N plus 1. I want to consider these two sequences. And I want to show that both of them are convergent, and this means that the whole sum is convergent. Okay. So you can see something. If you take first s to n plus 1 minus 2n, we're gonna get this b to n plus 1 minus b to n plus 2. It's easy to see here. Back to this one. If you take the difference s to n plus 2, this guy minus this guy, then b1 is going to cancel with this, minus b2 cancel with this cancel with this. Here you have minus b2n, it's going to cancel with that one. So you will be left with this term, which is b2n plus 1 minus b2n plus 2. And I know that b2n plus 1 is bigger than b2n plus 2. Why? Because the function is decreasing. So that means b2n plus 1 minus b to n plus 2 is bigger than 0, so it's positive. Okay, so when I take the difference s to n plus 2 minus s to n, I get b to n plus 1 minus b to n plus 2, which is a positive quantity, and this means that s to n is bigger than s to n plus 2. So s to n is increasing sequence. Okay, so this means the following, so this is increasing 0 less than or equal to s2 less than or equal to s4, etc. Okay, now I know my sequence is increasing. If I show that the sequence is bounded above, then by the monotone convergence theorem, this is going to be convergent. Okay, remember that if you look at the previous slide, you can see that S2n was written in this form. Okay, I will just try to rewrite it in a different form. So I want to group B2 and B3 together. So you put parentheses around them, you change the sign inside because you have negative outside, and so on. So I'm leaving this and this by themselves. Okay, now let's notice something here. B2 minus B3, this is a positive quantity. This is bigger than 0. This is bigger than 0. This is bigger than 0. And B2n by itself is bigger than 0. The reason is because the series or the sequence Bn is positive. And these are bigger than 0, what's in the brackets, because the Bn is decreasing. So B2 is bigger than B3. Okay, so you can see here that S2n is equal to B1 minus some positive quantity. So S2n is less than B1. And this is going to be the case for every n. So S2n is less than or equal to B1. So here I have showed two things. I have showed that S2n is increasing and S2n is bounded above by B1. Then by the monotone convergence theorem, this is a convergent series. What does it mean? That means that the limit of to convergent sequence, sorry, of S to n when n goes to infinity is equal to some number. S is a finite number. The limit exists. In a similar way, I can try to show that the partial sum for the odd with odd indices is also convergent. Now the partial sum with odd indices s2n plus 1 is positive and decreasing. Okay. Now why it's decreasing? Because you can take the difference s2n plus 1 minus s2n. Okay, and when you take the difference, you're gonna get negative b2n plus 1 plus b2n plus 1. Again, how do you take the difference? Well, you have everything listed here. Okay, so if you take s2n plus 1, if you take this guy minus this guy, okay, you're gonna get negative b2n plus b2n plus 1 as an answer. Okay. So that means that s2n plus 1 minus s2n minus 1 is equal to this guy, which is negative. The reason this is negative is because b2n is bigger than b2n plus 1. Okay, so 0 is bigger than, if you move this to the other side, which is negative b2n plus b2n plus 1. So that means this term is negative. So s2n plus 1 minus s2n minus 1 is less than 0. Move s2n minus 1 to the other side, you get this. So this means that s2n plus 1 is less than s2n minus 1. Similarly, you can show that this is less than s2n minus 3. This is less. This is less than s1. Okay, so this means that this is a decreasing sequence. Moreover, I know it's positive. So you have a decreasing numbers, decreasing sequence. I know it's positive, so it's gonna be above the x-axis. So it's bounded below by 0. Monotonic, decreasing, bounded below, again, by the monotone convergence theorem, it's convergent. Okay, so then the sequence is convergent by the monotone convergence theorem. Here you can visualize, like, what does it mean to say b1 minus b2 plus b3 minus b4. So you can see how b1 was bigger than b2, and then you take the difference, and so on. So we said that the even indices, they go to s. Okay. Now we can write s2n plus 1 as s2n plus b2n plus 1. Again, you can go back to here. Well, this is s2n. If you want to write after this, what's s2n plus 1? Well, s2n plus 1 is going to be everything plus b2n plus 1. So if you take the difference to get b2n s2n plus 1, you just need to add this. So that's the difference between them. So you can see that s2n plus 1 is s2n plus b sub 2n plus 1. Okay, now I know that this limit goes to s. Now I know that this limit goes to 0. Why? Because that's what we assumed. We assumed that bn is decreasing. We assumed that bn goes to 0 when n goes to infinity, and we wanted to show that it's convergent. So you see that the limit when n goes to infinity of s to n is equal to finite number. Limit when n goes to infinity of s to n plus 1 is a finite number. So the even and the odd partial sums converge to s, then the sequence Sn converges to s as well. Now, quick remark here, it's not necessarily that to use the alternating series test, it's not necessarily to show that Bn is increasing, or sorry, is decreasing for n greater or equal to 1. No, you just need to have a greater or equal to some value n. Okay, so this is a stronger condition. And then, of course, Bn has to be decreasing, positive always. So you can make this adjustment to the alternating series test. So it's not necessarily that it has to be decreasing from the beginning. It could be decreasing from some range, but indefinitely. Here's an example. I want to determine the convergence of this Alternating series. Now again, I want to write it like that. Summation from n equal 1 to infinity minus 1 to the power n plus 1 multiplied by 1 over n. So I want you to see something here, that this has exactly the form that we had in the alternating series test, with Bn is equal to 1 over n. Okay. Now let's look at the conditions that we have here. It's easy to see that 0 is less than or equal to 1 over n plus 1, sorry, is less than or equal to 1 over n. Why? This is Bn plus 1, by the way. Well, all the terms here are positive because n is always positive, so 1 over n is always positive. Now, Bn plus 1 is less than or equal to Bn. This is simple because they have the same numerator, but the denominator here is bigger, so the fraction is smaller. And this is true for every n. So we can see that the first condition is satisfied, which is Bn is decreasing. The second condition, you find the limit of Bn when n goes to infinity. This is the limit of 1 over n when n goes to infinity, which is 0. So the two conditions, condition 1, which is Bn is positive and decreasing. Condition 2 is that the limit of Bn goes to 0 when n goes to infinity. Then the series converges by the alternating series test. Converges by the alternating series test. Okay, so this is a nice example, and you can see that this is the alternating series of the harmonic series, which was divergent. So when you put negative 1 to the power n plus 1, when the numbers alternate positive and negative, then it becomes convergent. Here's another example. Again, this is very similar. This is going to be convergent for the same reason. Okay, because here Bn is equal to 1 over n squared. Clearly, it's always greater or equal to 0. 0 less than or equal to Bn plus 1, less than or equal to Bn, because remember that this is 1 over n plus 1 squared, less than or equal to 1 over n squared. So the first condition here is satisfied. The second condition is limit of 1 over n squared when n approaches infinity. That's equal to 0 as well. So by the alternating series test, the series is convergent. Okay. Now for that last one, notice that if you want to think about this as an alternating series, that's the sum from n equal 1 to infinity, negative 1 to the power n plus 1 multiplied by n over n plus 1, which is Bn. But one thing here you can notice, and there is no need to keep going, which is this. The limit of Bn when n goes to infinity is equal to what? This is equal to 1. Okay. So what does this mean? This means the following, that this guy at infinity, as n goes to infinity, the value of this term is not going to be 1. It's going to alternate plus minus 1. Why? Because when n is really large and it's positive, and it's going to alternate between even and odd. So every time you're going to have minus 1, 1, minus 1, 1, minus 1, 1. Now, it's multiplied by n over n plus 1, which is going to approach is 1. If this approaches 0, then you multiply anything by 0, you get 0. But here, this is going to approach 1. So as n goes to infinity, this term alternates between minus 1 and plus 1. Like if this guy was 100, that's going to alternate between minus 100 and 100. If this guy was 2, that's going to alternate between minus 1 times 2, which is minus 2 and 2. So the limit does not exist. The limit does not exist. And if the limit is not equal to 0, then it diverges by the divergence test. By the divergence test. Okay. Now, given a series, sum from n equal 1 to infinity, an, I don't know whether an is positive or negative, just this is a random series. We consider the following series, sum from n equal 1 to infinity of the absolute value of an. Now, certainly now, all the terms here are bigger than 0 because I'm taking the absolute value. So, a series sum from n equal 1 to infinity of an is called absolutely convergent if the series sum from n equal 1 to infinity of the absolute value of an is convergent. Okay, so this is the definition. So notice that if the sum from n equal 1 to infinity of an is a series with positive terms, so if all these are positive, then these two are the same. There is no point of talking about absolute convergence. Okay, so because the absolute convergence would be the same as the regular convergence. So the absolute convergence plays a role, or we are interested in this when I have negative terms. In other words, here when I have alternating series. So here's an example. The series sum from n equal 1 to infinity, negative 1 to the power n over n squared is absolutely convergent. Now just recall one thing. If you take the absolute value of negative 1 to the power n over n squared, this is the absolute value of negative 1 to the power n over the absolute value of n squared absolute value of this over this. N squared is positive, its absolute value is n squared. Now the absolute value of negative 1 to the power n is 1 because it can be negative 1 or 1. In either way, when you take the absolute value, it's going to be 1 over n squared. So this series is alternating. So when I take sum of an, when n from n equal 1 to infinity, I'm taking the sum from n equal 1 to infinity of this is an of 1 over n squared. And I know that this is a p series, I know it's convergent. So in this case, because this guy converges, then I say that the sum without the absolute value from n equal 1 to infinity, I say is absolutely convergent. Okay, so this is an example of an absolutely convergent series. This is an example of a series that's not absolutely convergent. We have shown earlier using the alternating series test that this is convergent. Okay, but is it absolutely convergent? No, because if you take the absolute value of the term, that's going to be 1 over n. And I know that the sum from n equal 1 to infinity of 1 over n is the harmonic series, which is divergent. Okay, so here we showed an example of a series that's absolutely convergent and a series that's not absolutely convergent. Now, we introduce here a new term, and this refers to the last example we just did. If a series is convergent, but when you take its absolute value, it becomes divergent. So that means when it's convergent, but not absolutely convergent, then we call it conditionally convergent. So a simple example that we just saw was this, sum from n equal 1 to infinity, negative 1 to the power n plus 1 over n. This is conditionally convergent. Why? Because we showed that it's convergent using the alternating series test, and we know that it's divergent. Its absolute value is divergent because two things. The first thing is the series from n equal 1 to infinity, negative 1 to the n plus 1 over n converges by the alternating series test. So by the alternating series test. And the sum from n equal 1 to infinity of its absolute value is equal to the sum of 1 over n, which is divergent because it's a harmonic series. Okay, so in this case, we say that the series is conditionally convergent, which means it's convergent, but it's not absolutely convergent. Theorem if sum from n equal 1 to infinity of an is absolutely convergent, then it's convergent. Okay? So this is a really nice theorem here. We know this. We know this inequality because this guy can be 0 when this is 0. This is 0 if an is negative. Like, for example, if you take any number, 0 is less than or equal to absolute value of -2 plus -2 less than or equal to 2 times absolute value of -2. If the number is negative here, this is going to be 0, and this is, and you're fine here, so you met the limit. If the number was positive here, so let's say I have 2, so this is 2 times absolute value of 2, then this is going to be 2, this is going to be the same, both of them are positive, so that's going to be equal to twice the positive value, or twice the absolute value. So this is a valid inequality. Sorry. Now, why I wanted this? Because I want to use the comparison test, and I cannot use the comparison test unless I know that the terms are positive. And here, if I just look at an is not positive. Okay? So I cannot say, oh, you know, an is less than or equal to this. If someone wants to prove it in this way, this is convergent, okay, then this has to be convergent. No, you cannot use it because this is not bigger or equal to 0. Okay, so that's why we have to be a bit more creative here. So we are considering this inequality. Now, we know that this is convergent. Why this is convergent? Because the statement here says if this is absolutely convergent, when I say this is absolutely convergent, that means I'm saying that the sum of the absolute value of n is convergent. This is absolutely convergent. By the comparison test, this is going to be convergent. Okay. Now, if this is convergent, then I can split the sum. Okay. Or I can make it in this form. I can use the fact that an can be written as absolute value of an plus an, which is a positive, minus an. Okay. So take the summation over all these, minus an in terms of absolute value. I know that this is convergent. I know that this is convergent. So this is going to be equal to some number s1. This is going to be equal to some number s2. You take s1 minus s2, you get s, some number. Finite number minus finite number is equal to a finite number, meaning that this is convergent. So now, if you have a series and you show that it's absolutely convergent, then automatically it's going to be convergent. Okay. Some examples here. State whether each of the following series converges absolutely, conditionally, or not at all. I can see that this is not at all. Why? Because this goes to 1 as n goes to infinity. That means that whole thing, okay, its limit is not 1, its limit does not exist. Again, why this does not exist? Because this is going to alternate between plus minus the value of that limit. So that's going to alternate between plus 1 and minus 1. Okay. Now, look at that one here. Sum from n equal 1 to infinity of -1 to the power n plus 1 times 1 over radical n plus 3. It's an alternating series. I know that this guy, if I call it Bn, I know that Bn goes to 0 as n goes to infinity because it's going to be 1 over radical infinity, which is 1 over infinity, and that's 0. So for and clearly this is positive, so Bn, which is 1 over radical n plus 3, is bigger than or equal to 0. So this is fine. Is it decreasing? Well, let's look at Bn plus 1. Bn plus 1 is 1 over radical n plus 4. Actually, this is less than or equal to 1 over radical n plus 3 because the denominator radical n plus 4 is bigger than the denominator radical n plus 3. So yes, I have the two conditions satisfied. The first one, 0, less than or equal to b sub n, less than or equal to b sub, sorry, bn plus 1, this is bn. So bn is decreasing, limit of bn is 0, then the series converges by the alternating series test. Converges by the alternating series test. Okay, but I want to tell whether it's absolutely or conditionally. So I'm done with the first part. I know it's convergent. Now the second part, I want to check its absolute value, the absolute value of the sum. Okay, so what I will do right now is I will check the limit when, not the limit, well, the sum. I want to check the sum, just 1 second here. Now I will take the sum from n equal 1 to infinity of the absolute value of negative 1 to the n plus 1, 1 over radical n plus 3. This is the sum from n equal 1 to infinity, 1 over radical n plus 3. We have done something like this before. This is divergent. This diverges by the limit comparison test. When you compare it to, you should know, to this sequence, to 1 over radical n. And we know that this is a p-series with p equal 1/2, so it's divergent. So what do we conclude here? For this one, we showed that it's convergent. We showed that it's not absolutely convergent. So as a result, it's conditionally convergent. Because it was convergent using the alternating series test, it's divergent if you use the limit comparison test and you compare it with 1 over radical n. This one clearly is divergent by the divergence test because the limit of cosine squared does not exist. For that one, again you have bn, so you can try this one. So this is bn here. Is bn does it converge, or is it increasing or decreasing? Well, bn plus 1 is equal to ln of 1 plus 1 over n plus 1. And bn is equal to ln of 1 plus 1 over n. I'll tell you something here, that the ln is increasing. If you recall about as a series, as a function, the ln has this function. Now, which one's bigger? 1 plus 1 over n plus 1 or 1 plus 1 over n? Well, 1 plus 1 over n plus 1 comes before it, because 1 over n is bigger. So the ln of this is less than the ln of this. So that's going to be ln of 1 plus 1 over n plus 1. And above this will be ln of 1 plus 1 over n. So bn plus 1 is less than or equal to bn. Is it positive? Yes, because ln of 1 is equal to 0. ln of 1 plus anything extra is going to be positive. Okay? And limit of ln of 1 plus 1 over n when n goes to infinity, this limit goes to 0 because this goes to ln of 1 plus 1 over infinity, which is 0. This is ln 1, so it's 0. So limit of bn is equal to 0. So this is convergent. Now, does it diverge? Does it converge if I don't take the absolute value? Well, you have to check this. So you still need to verify whether the limit, so here you still need to do this. We can do it in our live session, but you should try this out. Try to see whether the sum from n equal 1 to infinity of negative 1 to the of the absolute value of this, which is going to be absolute value of ln 1 plus 1 over n, and that's going to be just, no need for absolute value because I know it's positive, is, I have the feeling is that it's divergent. One way to do it, try to compare it with 1 over n, okay, and see what you get. So as a result, that's going to be conditionally convergent.